Hello viewers, welcome back to my channel DPC Smart, which is a YouTube platform for Days Physics Classroom. So in my previous lecture or previous video for the MAKAUT btech physics syllabus for the topic diffraction under the chapter optics, I have discussed about single slit diffraction and also calculated the resultant intensity distribution for single slit diffraction and found out the positions for maximum and minimum intensities. In this video, I will discuss about diffraction from double slits, and further I will also discuss about diffraction from multiple slits or diffraction from a grating. Similarly, here also we will deal with positions of different maximum and minimum in the intensity distribution for the diffraction patterns. In addition to these theory lectures, there are different numerical problems that also used to come in the MAKAUT btech physics semester question paper. To solve the numerical problems, you have to join my online problem solving classes. And if you are interested to join my theory classes as well as numerical problem solving classes and previous year questions and previous year numerical problem solving classes, you can join my online classes and you can contact me through the WhatsApp number given in the screen, and also you can directly message me through Instagram and Facebook account. All details are given in the background of my. So without wasting further time, let us start the class. So this is the syllabus for MAKAUT btech physics paper code PH101 or 201 under optics. In my previous video, I have discussed about different types of diffraction, Fraunhofer and Fresnel diffraction, single slit Fraunhofer diffraction and their intensity distribution. In this video, I will discuss about Fraunhofer diffraction from a double slit. So in my previous video, I have discussed what is Fraunhofer diffraction. That means in case of Fraunhofer diffraction, the source and the screen are at effectively infinite distance from the diffracting aperture. In case of double slit Fraunhofer diffraction, two slits each having width of A are separated by a opaque space B. So in this figure, these are two slits, slit 1 and this one is slit 2. So these two slits each having a slit width of A are separated by an opaque that has a width of B. So this is a opaque. So a parallel beam of monochromatic light of wavelength lambda is incident normally upon those parallel slits of width A and separated by a opaque space B. So after diffraction from these two slits, diffracted rays would be focused by a convex lens, and after passing through this convex lens, a screen is placed at a focal plane of this convex lens. So after passing through this convex lens, the diffracted rays will merge and they will produce diffraction pattern on the screen. So diffraction patterns are recorded on the screen. So here let theta be the angle of diffraction, A is the slit width, B is the opaque width, and here one important term is that is called displacement or distance between corresponding points. So distance between corresponding points is denoted as D, which is equals to A plus B. Now what are corresponding points? Suppose this one is slit 1 and this one is slit 2 with A, and this has a width also A, and this is the opaque B. Now corresponding point means if we take the middle of this slit 1, then its corresponding point will be also the middle point of the slit 2. So that distance between two corresponding point 1 and 2 becomes constant, that is A plus B. So D equals to A plus B, which is a distance between two corresponding points. Similarly, if we take one point at the upper part of this slit, then its corresponding point will also be upper part of this second slit. If we take one point here, the lower part of the slit, then its corresponding point will also be the lower part of the slit. So that distance between these corresponding points would be same. So it would be A plus B. That would be constant. And now in case of Fraunhofer double slit diffraction, the expression for intensity distribution is given by this one. I equals to 4I naught sin square alpha by alpha square into cos square beta. Its derivation is not in your syllabus. As you can see in your syllabus that only the expressions for intensity distribution and expressions for maxima, minima and qualitative discussion of fringes are only included in the syllabus. So the derivation of this intensity distribution for Fraunhofer double slit diffraction is not required as per your syllabus. Only the intensity distribution function and only qualitative discussion regarding the maximum and minimum intensities are included in the syllabus. So we will not discuss the derivation part of this intensity distribution. Now the expression for intensity distribution is this one. I equals to 4I naught into sin square alpha by alpha square into cos square beta, where alpha is, that is pi into a slit with sin theta, that is theta is diffraction angle divided by lambda, the wavelength used, and beta is pi d sin theta by lambda, where d equals to a plus b. So these three conditions. Now if you notice the intensity distribution function, then you can see that there are two parts together forming the intensity distribution, that is 4I naught sin square alpha by alpha square, one part, that is part 1, and second part is cos square beta term. Now if you notice the first and second term, you can see that you are already familiar with these two terms. Now what is the first term? First term is 4I0 sin square alpha by alpha square. So this term, first term, is related to diffraction pattern due to a single slit, that I have already discussed in my previous lecture and already derived that function, that for a single slit diffraction intensity would be this form 4I naught sin square alpha by alpha square. And similarly the second term cos square beta term also you are familiar with in the first lecture of diffraction, where there I have discussed about the double slit interference. So in case of double slit interference, the intensity distribution is proportional to cos square beta. So first term is related to the diffraction pattern due to single slit, and second term cos square beta term is related to interference pattern due to a double slit. So together they form the expression for double slit diffraction intensity pattern. তাহলে ইন্টেন্সিটিটা কি পাওয়া গেল? ইন্টেন্সিটিটা হচ্ছে দুটো টার্মের রেজাল্টেন্ট ইন্টেন্সিটি। একটা হচ্ছে ডাবল স্লিট ইন্টারফারেন্স প্যাটার্নের ইন্টেন্সিটি, তার সাথে অ্যাডিশনালি অ্যাড হচ্ছে ডিফ্র্যাকশন প্যাটার্ন অফ সিঙ্গেল স্লিট। সো টুগেদার এরা একসাথে ফর্ম করছে ইন্টেন্সিটি ডিস্ট্রিবিউশন অফ double slit diffraction pattern. Similarly, we have to calculate the positions of minima and maximum intensity. So for minimum intensity, that means I should be 0. So কি উপায় I 0 হতে পারে? First of all, first case it can be sin square alpha by alpha square 0. এটা স্যাটিসফাই কখন হবে? যখন sin alpha 0 or alpha equals to plus minus m pi, where m starts from 1, 2, 3 so on, but not 0. Why not 0? That I have already discussed in my previous video, that for when m becomes 0, that corresponds to principal maximum. To understand this, you may go to my previous lecture where I have discussed everything, that for m0 condition, sin alpha by alpha would be 1 when limit alpha tends to 0. So that will describe the position of principal maxima, not minima. For this part, you may refer to my previous lecture. So the position of minima would be when alpha equals to plus minus m pi, m starting from 1, 2, 3 etc. For that case, alpha means pi a sin theta by lambda, that would be plus minus m pi, pi cancels out and becomes a sin theta equals to plus minus m lambda. This is the condition for diffraction minima. So position of minima, first condition we have found out. Next we have to find out the second condition. Second condition means I would be also 0 when cos beta becomes 0. So cos beta, second condition is cos beta equals to 0. So what is the value of beta when cos beta 0? or cos beta is 0. That means beta equals to plus minus odd integer 2n plus 1 into pi by 2. Similarly, beta is pi d sin theta by lambda. So that would be equals to plus minus 2n plus 1 pi by 2. Pi cancels out. And we get d sin theta equals to plus minus 2n plus 1 lambda by 2. This is the second condition for diffraction minimum position. First condition is this one, second condition is this one. If either of these follows, then the resultant intensity would be position of minima, or resultant intensity would be 0. So the position of minima would be a sin theta equals to plus minus m lambda and d sin theta that is equals to plus minus 2n plus 1 into lambda by 2. These are the conditions for position of minima. Similarly, we have to find out the positions of maxima. So the positions of maxima means when m equals to 0, that is the condition for principal maxima. And when the second condition, that is second part, that is cos square beta term becomes plus 1 or maximum, that means cos square beta, that would be plus 1, or beta would be plus minus p pi. For beta plus minus p pi, p starting from 0, 1, 2, 3. For beta plus minus p pi, cos square beta would be plus 1. For that case, resultant intensity would be maxima. So beta means pi d sin theta by lambda, that is plus minus p pi. Pi cancels out. So d sin theta becomes plus minus p lambda. So this is the condition for position of maxima. So these are the conditions for position of minima. A sin theta equals to plus minus m lambda and d sin theta equals to plus minus odd integer into lambda by 2, and position of maxima is given by d sin theta equals to plus minus p lambda. So by following those conditions for maxima and minima, we can obtain the resultant intensity pattern. So the intensity pattern for double slit diffraction would be this one. Here it consists of two terms, that means interference pattern due to double slit and diffraction intensity or diffraction pattern due to a single slit. So as the resultant intensity consists of interference pattern due to double slit and a diffraction pattern due to single slit, so the resultant intensity distribution would be like this figure. So here this one is the interference pattern for double slit. As we know, that is cos square pattern, that is cos square beta pattern. If we plot along y-axis intensity and along x-axis beta, then it would be like this. Similarly, the diffraction pattern intensity or the intensity of pattern of the diffraction due to single slit would be like this figure. So this is the position of diffraction maxima, this is the diffraction secondary maxima, and these are the diffraction minima for single slit. Then the resultant pattern would be a mixture or the combination of these two. So the diffraction pattern will act as an envelope to the interference pattern, and resultant pattern would be like this or like this. So the diffraction pattern, this one is the diffraction pattern. So this is acting as an envelope to the interference pattern, and resultant intensity would be similar to this figure or this figure. That means these are the interference patterns, these, and this is the diffraction pattern. So resultant intensity would be, or resultant pattern would be combination of these two. That means the diffraction pattern functioning as a envelope to the interference pattern, and the resultant pattern would be this. So here one significant term will arise which is called missing orders. So in my next slide I will discuss about what is the missing orders. Now what are missing orders? In 2023 MAKAUT btech Physics Semester paper, it came as a question. When conditions for interference maxima and minima for the diffraction pattern occur simultaneously at the same position of theta. Then in the resultant intensity distribution, there will be no illumination. That means for that particular value of theta, the interference maxima will be missing, or the resultant illumination would be 0, or there will be no illumination in that direction of theta. Repeating again, when conditions for interference maxima and diffraction minima for a particular diffraction angle theta occurs simultaneously at the same position of theta, there will be no illumination on that particular angle theta, and in the resultant intensity the interference maximum would be missing. তাহলে ব্যাপারটা কি, যদি একটা পার্টিকুলার ভ্যালু অফ ডিফ্রাকশন অ্যাঙ্গেল থিটার জন্য যদি ইন্টারফারেন্স ম্যাক্সিমা এবং ডিফ্রাকশন মিনিমা সাইমালটেনিয়াসলি একই জায়গায় স্যাটিসফাই করে, তাহলে রেজাল্টেন্ট যে ইন্টেন্সিটি ডিস্ট্রিবিউশন আমরা পাবো সেখানে ওই পার্টিকুলার থিটা অ্যাঙ্গেলের জন্য কোনো রকম ইলুমিনেশন থাকবে না, পাওয়া যাবে না। অর ইন আদার ওয়ার্ডস আমরা কি বলতে পারি, ওই পার্টিকুলার অ্যাঙ্গেল থিটার জন্য ওই পজিশনে ইন্টারফারেন্স ইন্টেন্সিটি যে ম্যাক্সিমাম পাওয়া গেছিলো সেটা ওই পজিশনে মিসিং হয়ে যাবে। তার মানে কি, ডিফ্রাকশন মিনিমা ওই ইন্টারফারেন্স ম্যাক্সিমাটাকে সাপ্রেস করে দেবে। So what would be the condition? That means condition for diffraction minima and condition for interference maxima both are simultaneously satisfied. So what is the condition for diffraction minima? I have discussed in the previous slide, that is a sin theta becomes m lambda. That is the condition for diffraction minimum, and condition for interference maxima would be d sin theta equals to p lambda. So both are simultaneously satisfied. As a result of that, for a particular value of theta, the interference maxima would be suppressed over the diffraction minima, and there would be no illumination at that direction of theta. So both simultaneously satisfied means, if we make a ratio this by this, then we will get d sin theta by a sin theta, that is equals to plus minus p lambda divided by plus minus m lambda. Or sin theta cancels out, lambda cancels out, so we will get d by a equals to p by m, or d equals to a plus b, or we get a plus b by a equals to p by m. So this is the condition for missing orders. So which orders would be missing? So here A is slit width, B is opaque. Suppose opaque width is twice the slit width. So what would be the condition here now? So there would be the numerator part would be 2a plus a means 3a by a, and right hand side would be p by m. So a cancels out, that means p, the order of interference maxima p would be thrice the order of diffraction minima, p equals to 3m. That means if in case of first order diffraction m1, which orders would be missing in the resultant intensity pattern? That is third order, for m equals to 2 it would be 6, for m equals to 3 it would be 9th. So p equals to, that means interference order third, 6th, 9th, 12th, etc., that orders would be missing. So in the resultant intensity pattern on the screen, the third order, 6th order, 9th order, 12th order of the interference pattern or interference maxima would be missing when opaque space or opaque width is twice the slit width. So these orders would be missing, and these are called missing orders. So in the figure you can see here missing orders are 3. So in this figure, if b equals to 2a, then third, 6th, 9th, 12th orders would be missing. So similarly you can notice from this resultant intensity distribution that third order of the interference max, that is third order of interference maxima, is missing in the resultant distribution. So this order is missing. Similarly here also third order is missing. Similarly there will be 6th order, this third order missing there, again it will be 6th order missing, 9th order missing. All these are called missing orders. So this came as a question in MAKAUT 2023 semester paper. Next we will discuss about diffraction from multiple slits, or here we will discuss about one device that is called grating, which consists of multiple slits. So we will consider or we will discuss about diffraction from grating. Sometimes it is also called plane transmission grating. A diffraction grating is equivalent to a large number of parallel slits having equal width and separated from each other by equal opaque space, and it is made by ruling a large number of equidistant parallel lines on a plane glass plate. Well, plane transmission grating বা শুধু grating বলতে আমরা কি বুঝি? Large parallel numbers of equidistant slits যাদের width হচ্ছে সেম এবং they are separated, তারা আলাদা থাকে কি ইকুয়াল উইথের ওপেক স্পেস থেকে। এইরকম একটা ডিভাইস যার এই প্রপার্টিটা আছে তাকে বলবো আমরা গ্রেটিং। এবং গ্রেটিংটা কীভাবে তৈরি করা হয়? ডায়মন্ড রুলিং করা হয় একটা অপটিক্যালি প্লেন গ্লাস প্লেটের ওপর এইরকমভাবে, যাতে রুলিংসগুলো হয় প্যারালাল টু ইচ আদার এবং রুলিংসের প্রত্যেকটার উইথ হচ্ছে সেম এবং দে আর সেপারেটেড বাই ইকুয়াল উইথ অফ ওপেক স্পেস। So this is how gratings are prepared. Now there are some few terms related to grating. Number one is grating element and second one is grating constant. So first one is grating element. Grating element means suppose A be the slit width, that means A be the width of the slit and B be the opaque width. That means B is the distance between two slits. So that D equals to A plus B becomes constant, and this is called grating element. That means distance between two corresponding points which is equals to D, and that is equals to A plus B, that is sum of the slit width and opaque width, that becomes constant, and this is called grating element. So D, small d is called grating element. So this is the figure or for diffraction from a grating, that the multiple parallel slits are formed by diamond ruling on a optically plane glass plate that acts or functions as a grating. So parallel, a beam of wavelength lambda, monochromatic wavelength lambda, falls upon it, and after diffraction they produce diffraction pattern on the screen. So the grating element is simply the addition of or sum of slit width and opaque width, which is also the distance between two corresponding points. That is called grating element. Now we will find out another term is there, that is called grating constant. Grating constant means the number of such lines present in the grating per unit length. That means per unit length কতগুলো লাইনস আছে ওইরকম বা কতগুলো স্প্লিটস আছে পার ইউনিট লেন্থে একটা গ্রেটিংয়ে, দ্যাট ইজ কল্ড দ্য গ্রেটিং কনস্ট্যান্ট। সাপোজ পার ইউনিট লেন্থে বা পার সেন্টিমিটারে সাপোজ নাম্বার অফ সাচ লাইন ইজ n, then n is called, that is number of lines per centimeter or per unit length, capital N, and then n is called grating constant. Then there is a relation between grating constant and grating element, and that is n equals to 1 by d or d equals to 1 by n. That is the relation between grating element and grating constant. Now how to derive it? Suppose these are the slits and these are the opaques. Now we have considered three such parallel ruling. This is ruling 1, ruling 2 and ruling 3. So in between these three opaques there will be two such slits. So these are opaques. So in between three such opaques there will be two slits, slit 1 and slit 2. Now according to the distance between two corresponding points, suppose this one is first point, so its corresponding points would be this point, and distance between them is called grating element d, which is a constant. So in d, in the distance between d, number of ruling is 1. So in d distance number of ruling holo 1, তাহলে unit distance number of ruling would be 1 by d, and according to the definition of grating constant this is n. So this is how n becomes equals to 1 by d or 1 by grating element. Several numerical problems used to come in the MAKAUT B semester question paper regarding grating and the grating element, grating constants. For those numerical problems, you may join my online classes. In these lectures, I have not discussed the numerical problems and previous year numerical problems or previous year questions. So for that, you have to join my online class. Next, we will discuss about the expression for intensity distribution in grating. So this is the expression for intensity, resultant intensity in case of grating having n number of lines per unit length. Its derivation is not included in the MAKAUT btech physics syllabus, so I am not discussing it here, just only the expression is needed. So I equals to 4I naught sin square alpha by alpha square into sin square n gamma by sin square gamma. Here also it consists of two terms. First term is this one, that is term 1, and second term is this one. Similarly, the first term is related to diffraction pattern due to a single slit, and it acts as an envelope like the previous one, like the previous double slit diffraction. The first term is related to diffraction pattern due to a single slit, and second term is related to interference pattern due to n number of slits. So together they form the resultant intensity distribution. Here alpha is pi a sin theta by lambda and gamma is pi d sin theta by lambda. So alpha is pi a sin theta by lambda, which is related to slit with a, and gamma is pi d sin theta by lambda, which is related to the grating element d. So similarly, in case of grating, we have to find out the position of maxima. So to find out the position of principal maxima or the direction along the principal maxima, we have to take a plus b sin theta equals to plus minus m lambda. So this is the envelope function of the diffraction. So for principal maximum, a plus b sin theta would be plus minus m lambda, where m starts from 0, 1, 2. 0 means m0 means which is related to 0 order diffraction or central maximum. That means this is for m0. Similarly, m1, 2 would be first order maxima, second order maxima, and so on. And the resultant intensity distribution would be this figure. So along y-axis intensity, angle of diffraction. The resultant intensity would be this one. Next, from the condition of maxima, you can also calculate the maximum number of orders that are available for a grating. So to find that, what we have to do, we know the condition for principal maximum is a plus b sin theta equals to plus minus m lambda, where m starts from 0, 1, 2, 3, etc. Now m becomes, from here the order number m becomes a plus b sin theta by lambda. Now sin theta has a maximum value of plus 1 at theta 90 degrees. So sin theta plus 1 means m would be m max, that would be a plus b by lambda. So now total maximum number of orders jeta pawa jabe for that grating would be m max equals to a plus b by lambda. That means d by lambda. Now what are the applications of this grating? First of all, the diffraction grating or diffraction grating acts like a prism-like device that used to separate the light into several parts. Now, how a diffraction grating will act like a prism and it will separate lights into parts, that I will discuss in the next video. There I will discuss about resolving power of a grating and the conditions that should be satisfied by a device to resolve a spectrum, etc. For now, you just know the application of grating is the diffraction grating acts like a prism to separate lights into several parts based on the wavelength. Secondly, diffraction gratings are used in the systems needing a high resolution separation of wavelengths. For example, most common use is laser. Eta high resolution eta ki kore prothomoto prism er moto act kore. Secondly ki hoy different wavelength ke separate korte eta kaj korano hoy. For example hocche laser. Thirdly, polychromatic light ke or multiple wavelength er light it used to convert into monochromatic light, and other common uses are in form of spectroscopy, which use diffraction gratings to separate unknown source of radiation into its spectra. এই চারটেই হলো main application of grating. Prism like device, secondly high resolution separation of wavelengths, thirdly polychromatic to monochromatic light conversion, fourthly in the form of spectroscopy, diffraction gratings are used to separate unknown source of radiation into its spectra. So these are the applications of grating. In the next video, I will discuss about what is resolving power and what are the resolving powers of different gratings, and using resolving power of a grating, how the grating can be used as prism or to separate different wavelengths or to provide a monochromatic source from a polychromatic light using grating. So this is the end of this video. See you in the next video. Till then, bye.